And thank you to the organizers for giving me a chance to present this recent work. So basically, this is, I'll try to give some motivation for new analysis of, well, in my application it will be electromagnetic media, electromagnetic composites, but I believe that the method is applicable to a wide range of contexts, right, including acoustics and other wave propagation contexts, possibly electromagnetic wave propagation through liquid crystals, for example. Basically, the sort of the underlying, one of the underlying goals is to try and understand what a metamaterial is. Almost exactly a year ago, there was a meeting in Minneapolis where Dick commented in one of the talks that metamaterial is what people used to call composites. So I'll try to explain what a metamaterial is, which in a way which I think I have finally understood personally. So I think I have a definition of what it is. So basically, it's not just any composite; it's a composite with a resonance, micro-resonance effect. And I will try to show how, more or less, well, I hope it will get somewhat clear how micro-resonances can lead to a metamaterial behavior. By metamaterial here, I mean frequency dispersion, and if we talk about the time domain, it will be what people call time dispersion or time non-locality. So by some kind of multi-scale analysis, so I don't even want to use the word homogenization anymore, we obtain composites with memory, or in the frequency domain with frequency dispersion, and eventually, hopefully this will, as one potential application, this will lead to full electromagnetic, so full Maxwell with permittivity and permeability that could be negative, both negative at the same time in some frequency intervals, which is what people know as negative diffraction, right? So this is this paper by Victor Veselago is often, very often quoted as a precursor of the modern interest in modern activities in metamaterials. So he theoretically predicted the existence of media with both permittivity and permeability negative at the same time, right? So there is no, this assumption does not contradict any laws of physics, and indeed, well, in the last 20-25 years, several recipes have been produced to manufacture such media, well, in the real world. And here, what I'm going to present is concern some recent attempts to understand how such media emerge in any process, more or less any process of multi-scale analysis, provided we make certain assumptions underlying assumptions about the composite. And these assumptions, in particular, will mean that we're dealing with some resonance effect, or if you like, some length scale interaction. So, as the rule of thumb, I think in any problem, as long as you have, so in order to get a metamaterial behavior, you would have to come up with a situation where there are two lengths which are of the same order. So, and then there will be some sort of frequency dispersive behavior. And I will produce one such example in this talk. So with this, I'll just show, this is the kind of classical picture that you often see when in talks on homogenization. But I'm trying to move away from using the word homogenization because sometimes people think about homogenization as a long wavelength approximation, or right, or small frequency approximation. So I don't want to get tied to that notion. Okay, so first I will give some motivation, and motivation will come from several sides. So I forgot to mention that this is joint work with Yulia Yershova, who was in Bath until recently, and now it's in Pittsburgh. And Alexander Kirill, who sits in Pittsburgh. And some details, I won't be able to go into much detail on the technique, on the analysis, but the details are here. Okay, so the first motivation is in what was already mentioned as the sort of now classical homogenization theory. So as a prototype problem, let's think of a scalar equation of this kind. So we're interested in the asymptotic analysis of solutions to this problem. The right hand side, let's say, is an L2 in the whole space. D can be 2, 3, 1, and we assume that Z is not in the spectrum of the differential operator that is generated by this differential expression in L2 on Rd. Okay, so one result that has motivated us greatly is goes back to 2004, when Mikhail Bierman noticed that the homogenization process, as people had known it, can be viewed as a process of analyzing some perturbation so analyzing a family of operators associated with this operator in L2 on Rd by suitable direct fiber decomposition in terms of some perturbation analysis, right? And they came up with the notion of the spectral geom, which is what we know as the homogenized matrix. This in particular, identifying the spectral homogenized matrix in the spectral geom, has allowed them to prove this estimate for the first time. And this is the kind of thing that I believe should be taken as the modern homogenization principle. So what we are asking for is the description, some asymptotic description of these fields, so that the convergence holds in the operator norm sense. So earlier estimates would be of this kind, right? So this constant depends on f somehow, but of course, a priori, before we prove this, there may be sequences of right-hand sides f with norm 1 for which this constant goes up. So this is much better than this, and this kind of estimate implies important results, has important consequences for wave propagation, in particular the spectral convergence automatically, the convergence of spectral projections and the corresponding group of operators, so for the hyperbolic and parabolic equations and so on. So this is the kind of statement that we would be looking to establish, but as I will show in media, in resonant media, you have to relax the requirement that there is a limit function. So it will be an asymptotics still. So the function U naught, the homogenized solution, will have to be replaced by a sequence. U naught epsilon, you will ask what's the difference. I can just put U epsilon here, but it's like in the classical notion of asymptotics. So it's a bit subjective, a bit vague as to what we choose to be a criterion, for something to be an asymptotics of the asymptotics of a function, or n asymptotics. There is no unique choice, and it will be similar here as well. So one important assumption that they made, yes, and I didn't mention that this matrix here is Q periodic, where Q, by Q I will mean the unit cell. Okay, so an important assumption of uniform ellipticity, right, is something that is required to establish this result. So what about high contrast, what people have known as high contrast? So A is actually a parameterized family of matrix, and the way it depends on the parameter violates the assumption of uniform ellipticity. So this is our target. This is for the question mark here. We'd like to understand the corresponding asymptotic behavior. So in particular, if one tries to use asymptotic expansions, to scale asymptotic expansions, one ends up with this idea that with understanding that there is no single limit field. It has to be a two-scale function. It still depends on the slow and fast variables here. And this function U0 solves now two-scale system. So this was a fairly detailed analysis of this kind of asymptotics was done by Vasily Zhikov in 2000, which also served as a great motivation for us. However, Zhikov does not obtain estimates of this kind. So your epsilon minus U0 of x, epsilon epsilon here, bounded in this way, does not follow from his. In a way, it cannot be achieved, I argue, using the methods that he and some other people have been using, the method of two-scale convergence in particular. So I think I'm going to venture to say that what we propose, the new method, is doing much better than the two-scale convergence, even strong two-scale convergence. Okay, so what about trying to get an estimate like this? So this is the first work in this direction under no assumption of uniform ellipticity by myself and Shane Cooper in 2016 in a paper in Armor. So the answer is yes. Answer to this question, yes, we can obtain this estimate under some assumptions on the cell geometry. And essentially, the assumption is that the distance from what we call the soft component of the medium to the boundary of the unit cell is positive. So this is the main assumption, and this assumption was also made in the paper by Zhikov in order to obtain spectral convergence. So the soft component would be the part where the coefficient A, which now depends on epsilon, degenerates asymptotically. So here A epsilon does not satisfy this bound. And this part it does. And this is what we call positive. And the union is our cell Q. So under this assumption, we get the estimates. So and what about other geometries? For example, in the applications in electromagnetic applications and applications to say photonic crystals, you may have fibers where this assumption is not satisfied. So what about other geometries? And can we use some operator theoretic approaches here in order to try to answer this question. Okay, so the second motivation comes from, already mentioned this, what people call time dispersive media. Or media that possess memory. There is a memory convolution, time convolution integral here involved. So the classical Maxwell system is called in X of H is the derivative in time of B, and called E is minus the derivative in time B, right? So H and E are magnetic and electric fields, and D and B are the displacement and the induction. So the constitutive laws that need to complement the system, right, are in general of this form. So this is what physicists working in electromagnetics use all of these days. These are convolution integrals. I'm going to use this letter epsilon, not to confuse with that with a small parameter epsilon here. So this is a time convolution, and B is time convolution of mu and H. Okay, so in Fourier transform in time gives us curl H hat is I omega epsilon hat dot omega E hat and curl E is minus I omega mu. Okay, so I'm going to refer to this as 2. And in particular, if we assume that we're in a kind of fiber geometry, so this is a scalar matrix with coefficients that depend on x1, x2, but not on the third variable, and epsilon is some, we can think of some constant, let's say. So there is no memory in epsilon. And consider for simplicity t waves. So what does it mean? It means that h hat is 0, 0, h3 hat, and e hat is e1, h2 hat, 0. Then the equation 2 is reduced to minus divergence epsilon tilde inverse grad h3 hat equals omega squared mu hat omega h3 hat. Okay, so more generally for the full Maxwell, we will get both mu hat and epsilon hat frequency dependent frequencies here. It's in this equation, and this is what tells us that, well, hopefully, if these functions can become negative for some frequency intervals, we can make both of them negative sometimes. The problem is that there has been very little theoretical understanding as to how to obtain this by multi-scale analysis, this kind of epsilon hat and mu hat. So there is a lot of experimental recipes, and half of them. So if you look at the abstracts of conference talks in physics on this subject, there will be a word resonance present in them. So of course physicists understand very well that there is that one requires some kind of resonance, and this is, so our work is sort of a mathematical effort to try and understand that and predict explicitly so how these negative properties will emerge as a result of the assumptions, from the assumptions on the geometry and on the material properties. So in the end we will get actually a more or less explicit formula for epsilon hat and mu hat, but starting with a composite medium which is not frequency dispersive. Okay. So what was one of the things that motivated us looking at the paper by Vasily Zhikov that I mentioned is of course to take so here I still use the word homogenize because Zhikov used it. I try to distance myself from it now. So 8 epsilon was assumed to be, I'm just writing it in using the notation above to align myself with it, but Zhikov's notation was slightly different. So in the stiff part, the coefficients still satisfy the condition of uniform ellipticity, and in the soft part, they degenerate. Well, for simplicity, let's take them to be epsilon squared. Y squared, well, this is precisely the case when the wavelength in the, let's call this inclusion in the soft part, becomes comparable to the size of the part, to the size of the soft part itself and of the cell. So it's the same order of magnitude, and that's why the scaling has to be epsilon squared here. So well, using the above notation, U epsilon, which was at the very beginning, would be H3 hat, right? I'm just trying to establish a one-to-one correspondence between these objects. Z would be omega squared, and then U epsilon converges in the strong two-scale sense to U naught, which satisfies, so let's call it H0 hat 3, which satisfies this homogenized equation. So this is Zhikov's result. With some non-trivial but explicit function beta of omega. And the function beta looks like this, qualitatively. So there are some points identifiable from the Dirichlet-Laplacian on the inclusions here, where one will have asymptotes. And then elsewhere the behavior is like this. So beta does take negative values in these intervals. And so, of course, one can try to dream of the full Maxwell equation where we will have two betas, one of them describing the effective epsilon, the other describing the effective mu, both of them being negative somewhere. And epsilon home is just constant matrix. Okay, so the question for us is really, can time dispersive media be obtained as a result of homogenization, or multi-scale analysis, if you like. And this is the second one. And finally, the third one, which is I find also very exciting, concerns some observations about time dispersive media, where these assumptions are made from the start. Right? So our goal will eventually be deriving such constitutive laws by homogenization. But if one assumes such constitutive laws from the outset, then one can show, well, this is more or less standard stuff. Now you can find this kind of things in some books on electromagnetics, of which there aren't many, I must say, on mathematical electromagnetics. So by introducing, so I'm going to assume that epsilon hat is just 1 and mu hat is what corresponds to what people describe Lorentz media. So this is the dispersion. So this is Lorentz media. Okay, so if we introduce P and M, which are called polarization and magnetization, right? In this way, in the original system of Maxwell equations, and then do Fourier transform in time. Then actually the system 2, which is not here anymore, but it was a system with epsilon hat and mu hat frequency dependent, is equivalent to a kind of classical form, we call it Schrödinger form of the problem, where the dependence on omega is linear, and where A is self-adjoint derivative. So and U hat is actually H3 hat E1 hat E2 hat in the application to the TE waves. So it's a 6 vector. Okay, so the question is, one can view this as a self-adjoint extension, out of space extension of the problem with dependence on omega, and such objects have been studied in the abstract operator theory since 1940s, but they have not been picked up a lot in the analysis community and well, in the applied analysis community. And our guess is that if there is a link between the time dispersive Maxwell, that was equation 3, and this Zhikov problem, F4, then 4 should have a self-adjoint out of space extension. Or conservative, if you like, conservative out of space extension. So and the question for us is, can it be obtained? Can this extension, the extension, be obtained by asymptotic analysis of this problem, the one that we started with, right here in this in that example above. Okay, and well, all the work that I'm presenting is actually answering, giving a positive answer to all three questions. Okay, so this was the motivating part. So I'll just mention quickly that this is, of course, by far not the only way to create microresonances. So in order to obtain this type of dispersive frequency, dispersive behavior. I think this the statement that we attain are fairly general in the sense that in many, if not all, other situations where you have resonant inclusions in which the wavelength becomes comparable to the size of the inclusion, we will get the same kind of function beta, and it will be possible to write it explicitly under minimal assumptions. So we will no longer have make any assumptions about the geometry. So we will not be assuming that Q soft has a positive distance to the boundary. So, for example, one could well, I should put a tick here, right? It still includes the situation, but one could have I don't know something that something like this maybe. Or something more complicated. In 3D, you can have two intertwining structures, none of which has a. I mean, here already, none of them has a positive distance to the boundary, but we can have something more complicated. And the algorithm, more or less, it's very constructive. The algorithm is always the same, and in fact, I think I can now, by looking at the problem, I can guess what the answer is going to be. Because there are essentially two key ingredients to obtaining the answer. Where plus then, of course, in order to get the error estimates, you have to carry out you have to do the analysis and obtain these estimates. But if you don't care about the estimates, if you believe they hold, then you can write the answer right away. Okay, so the first step that I will make in order to get to move towards this homogenized description is what people sometimes refer to as Gilford transform. So we map functions in O2 to functions that live on the unit cell. And this is just an appropriate scaling, but depend on a parameter which I call T. So that the original problem, which the operator of which I will refer to as a epsilon, is converted into a family of problems that depend on a parameter, either T or a scaled version of T, which we call tau. And this is a family of transmission problems. Okay, So handling and transmission problems. So for each value tau in what people call the dual cell, so we had Q prime is the dual cell where the parameter lives. And in applications to polarize Maxwell D equals 2, but I'll keep D here for the dimension. So So, well, let me call this U plus, this U minus, but these are two components of a function, right? Of a function which lives in H1 on Q, and is H2 in each component. That I'll call the interface gamma. And a version of the Neumann operator, right, which is the jump of the corner derivative. Has to be 0. So m plus and m minus are just the opposite opposites of each other. This is the normal to gamma. Okay, so this is just a kind of the last bit of the setup that I need in order to formulate the main result. So our main result involves what people may call the so-called Stiklov problem on the stiff component of the composite. So this is one of the things that I feel I need to solve in order to be able to guess what that final formula is going to be. So initially, this problem was introduced in the late 19th century by Stiklov, who studied problem for a fluid with a free boundary, and the problem is this. So for each tau, you need to solve. You basically need to study this eigenvalue problem. Okay, so it's an eigenvalue problem where the eigenvalues would be thought of as the parameter in the Robin boundary conditions. So you're looking for non-zero solutions for those mu for which this problem has a non-zero solution u. So of course okay, so mu's, the eigenvalues, will depend on tau, and let's consider the lowest eigenvalue. Let's call it mu tau, and the corresponding eigenfunction. then it's not difficult to see that just using a sort of classical perturbation argument, it's not difficult to see that mu tau has this kind of expansion in powers of tau. Well, of course, this mu star will take an important part, will play an important role in the final answer, and sort of in the moderate contrast regime where the inclusions and the matrix have the same order of A with the same order of magnitude. This there would be an expansion of this type as well involved, although. Well, the Steklov problem is relevant only for the high contrast problem as it stands. But such expansions emerge, of course, in the analysis of Biermann and Sustena, and this is precisely the sort of object that they would refer to as the spectral germ. Okay, and so our result is that there is a controlled, uniform operator non-resolvent estimates. So I'll explain what this capital theta is. Between the original family, so this after the Gelfand transform, for us this is still the original family. We want to study it asymptotically, and this is the result of that analysis. And I will give an explicit description for this. So this is an estimate in the operator norm, and this 2/3 comes from the way in which I will simplify this expression for A to a home without going into details. I mean, one can write different versions of this. In particular, a more complicated version than that. Which I will present, where the estimates are with epsilon, with the power 1. But importantly, this estimate is called uniformly in tau, living in the dual cell, and this is an ingredient which is missing in the two-scale convergence approaches. Okay, so. In fact, for much of the time, I think in most cases, two-scale convergence approaches will only pick up the information that corresponds to small values of tau, possibly tau equals 0 most of the time. And this is the kind of long wavelength approximation that people know as homogenization. But I think the right way, the better way of doing this would be to look for an approximation which is uniform in tau. And here, this is just to say that this estimate, as I claim that it holds in a compact, also uniformly in Z, in a compact subset of C, complex plane, away from the spectrum. Well, I'll just put that the distance to the real axis is positive. Okay. So, and theta is just theta. This operator, this approximating family, will live in the space L2 of Q soft plus the complex numbers, one-dimensional. So and theta is just a partial isometry between L2 of Q and this space. So it vanishes on the orthogonal complement of this in L2 on Q. And on this subspace, it is an isometry. Okay, so what about A2 home? Finish it now, right? So I'll just write quickly what A2 home is. So the A2 home is an operator with this domain. So two component vectors, where the first component lives in H2 or Q-soft. The second is a complex number, such that these functions have the boundary values related to alpha explicitly via the zeroth eigenfunction of the Stickler problem. And the action of this operator is given explicitly so, I mean, if you look at it for a couple of minutes, you see that you can actually study it by hand. This operator. So this is also in gamma, the inner product, right? Minus again, these are just constants that are here. Explicitly, we have epsilon to the -2 mu star over tau alpha. Okay, so if one performs the inverse Kilfan transform, so we have done the direct Kilfan transform. Now we will look at this family, and we'll go back to compare the result of the original operator A epsilon in the whole space. We will obtain this corollary. So if we have if we observe the behavior of the original medium from the stiff component, so I sandwich the resolvent of the original operator A epsilon by projections onto the stiff component. So this is a periodic repetition of contractions of Q stiff to the whole space. So this is the stiff component of the original composite. So I restrict to it, I take the resolvent, and then I take a projection onto the space. So think of an observer which is sitting on the stiff component and is measuring the response, what happens, without maybe knowing about these resonant inclusions. Then up to some isometry, this theta home is just an isometric mapping. This is operator close to what people would call a generalized resolvent. So you don't have Z, instead you have some function B of Z of some operators with constant coefficients. So this is L2 to L2 in the whole space, right? Again, bounded in a controlled way. Where a home has constant coefficients, is an operator with constant coefficients. But more interestingly, we have an explicit formula for the function B. And this will be the last formula. Which coincides with the formula of Zhikov. but of course he didn't have estimates like this. So these lambda j's are the eigenvalues of the Dirichlet Laplacian on Q soft, and phi j are the corresponding eigenfunctions. So I mean, if you plot this, of course you will have a picture as shown earlier for the function, typical function beta. Okay, so I guess I'll wrap up at this point. So this is our answer to this question a year ago. We were already working on it. It was just a coincidence.
Thank you very much.
Thank you.
Yeah. Well, I'm not sure I understood the question. Any questions?
How does this connect to the kind of typical design where you have a split ring resonator or something like
Yeah,
that?
well, it is connected. It needs to be written down now.
Yeah,
It's
can you improve on that too?
Of course, yeah. So I mean, split ring resonators have been studied using two-scale convergence, and it's not even guaranteed that the results of our colleagues who are using two-scale convergence are valid, really are correct for, say, the scattering problem, I argue. Because the statement, the kind of statement that they make is that the sequence of solutions U epsilon converges to scale, let's say in a strong two-scale sense, to a function U naught which solves such and such problem, right? But it's not clear whether the two-scale convergence implies the convergence of the corresponding scattering operators, for example. So there is a hypothesis still that the limit problem that they obtain is the correct scattering problem. It's a nice hypothesis. I mean, it might well be true, but it's a hypothesis nonetheless. And our approach will be able to prove such statements. Because, well, I haven't had a chance to go into the details of the analysis, but it actually links naturally to the scattering theory. Well, in the spirit of Lux and Phillips, for example, going back to the late 50s, early 60s.
Further comments, questions? Okay, let's thank Kirill again.
Okay, thank you.